Hello, I'm just going to go through these last 3 examples of chapter 3. So to start off with, we've got the reminder of the Maclaurin series for the exponential function. We want to use Taylor's inequality to see how good this approximation is if we just use these first 3 terms of the series, as long as we're only looking at x values between -1/10 and 1/10. Then we're going to see what range of x values our approximation may be good enough for within 0.1. So for part A, to start off with, I've just started kind of expanding out the series. And the approximation that we're given is just these first 3 terms. So the approximation being the first 3 terms is t2x. Remember that index means that it's the highest power of x in the polynomial. Although, we had that example with sine where we could go one more, but here, you couldn't do t3, we'd have to do t2. Then we can write that e to the x is equal to this degree 2 polynomial plus the remainder, so all of those terms after it. So to be specific, r2x is equal to x cubed over 6 plus x to the 4 over 24, and so on. I'm just expanding out the factorials there. Then the error of the approximation is going to be the size of the remainder. By Taylor's inequality, we can get an estimate for how big this remainder is. So Taylor's inequality tells us that the absolute value of r2x is less than or equal to m over 3 factorial times absolute value of x cubed, where m is a number such that the absolute value of the third derivative of f is bounded above by this number m on the interval. So we need to find m. And to do that, we need to actually look at what the third derivative is. Well, our function is just e to the x, so the third derivative is just e to the x. And since we're specifically looking at when absolute value of x is less than 1/10, we can say that e to the x will be less than e to the 1/10. So we can choose m to be e to the 1/10. Then, by Taylor's inequality, we can say that this remainder is bounded above by e to the 1/10 over 3 factorial times x, absolute value of x cubed, which, given that absolute value of x here is less than 1/10, because that's the interval we're looking at, we can replace the x there with 1/10. So we have 1/10 cubed. And if you find what this number actually is, it's 0.02. So approximating the exponential function just with that quadratic polynomial, as long as we're only looking at x values within that little interval, it's a pretty good approximation. So that's cool. Then here, I guess I'd started erasing it or something. So we wanted to find when the remainder is bounded above by 0.1. Well, this is, the same type of remainder problem that we've done before, where we can replace the remainder with its upper bound, because we know this is bounded above by m absolute value of x cubed over 3 factorial less than 0.1. Then here, our interval is, let's say, x between negative a and a. Then we know that this would mean that e to the a would be our upper bound for m. And then here we've got a cubed less than 0.1. And then you can solve for a. I guess this isn't, let me see. I think I didn't actually do this one in class last year, so I don't have the solution worked out. But I think this is one, because we've got both a and an exponential function, this is one that you kind of like can't solve normally. So I'm just gonna get us a, like you can't solve it just like algebraically. So I'm just gonna quickly open up something on my computer to help us here. So we've got e a divided by 6 times x cubed. When is that less than 0.1? Well, Wolfram Alpha says that absolute value, or okay, Wolfram Alpha says that a would have to be less than 0.673771. And so that means that the interval that we could look at is negative 0.673771 to positive that. This would, of course, not be an exam question or even a homework question. I don't like giving you things that you need a calculator for because, I mean, you can't even do this with a calculator. You know, it's got that product log function in it. So, yeah, that's the idea. Okay, so example 4. We've got to find the Maclaurin series for the function f of x is equal to sine x, and then use that to find what the nth derivative of the function is at 0. So if we use what we've got already, well, we already know what the Maclaurin series for sine x is. We know that sine x is equal to the absolute value from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And so f of x is equal to x sine x is equal to x times that. And so we just pick up an extra power of x. So now in the numerator, we've got x to the 2n plus 2 instead. Cool. Well, now to find what the nth derivative of the function at 0 is, we need the summand, so what's inside the sum, to be of the correct form. Because we know that a Maclaurin series is of a certain form. Okay, we need summand to be of the form. So I'm going to just use k here so that we don't get too distracted by different n's meaning different things. So we need it to be the kth derivative at 0 over k factorial times x to the k. So here, we've got something kind of weird here, right? We've got the 2n plus 2. So what we can do is, let's say we shift indices a little. So what we'll do is we'll start the sum at n is equal to 1, reduce n by 1 inside sum. So this little like re-indexing trick. So that gives us that x sine x is equal to, so just increasing the starting index by 1. And then everywhere else inside the sum, we reduce it by 1. So we have negative 1 to the power of n minus 1. Then 2n plus 2, because that's equal to 2n plus 1, it now becomes 2n. So we have x to the 2n. Then over, so 2n plus 1, that's now going to become 2n minus 1. Again, because we've got like the 2n, so it's more dramatic of a change. Okay, so now we can try to compare this a little bit better to what we've got. Now, because we've got only even powers of x, we can see that that already tells us what the nth derivative is for odd powers. So because we only have k equal to 2n even, this means that the kth derivative of this function at 0 is equal to 0 for all odd k. So we could also write it as saying the 2n plus 1th derivative, because 2n plus 1 is odd, of this function at 0 is equal to 0. Then for the even ones, let's see if we can kind of make it fit the template we want a little bit better. So looking only at k is equal to 2n even. Actually, I'm just going to switch this page. Okay. Basically, here we've got f, 2n plus 1th derivative at 0 over 2n factorial times x to the 2n. This is like what we technically have. And then on the right-hand side, I'm going to put what we actually have. So this is what we actually have. And this is like the template. Okay, so using this, we need to try to find what f2n is, the 2nth derivative of the function. Here, we don't have the same thing in the denominator. So what we can do, oh, oops, sorry, I just realized I put x to the n there. It should be x to the 2n. Okay, let's ignore the x to the 2n's for now, because we're just looking at the coefficient. And so this tells us that f to the 2n at 0, 2n factorial, okay, that should be equal to negative 1 to the n minus 1 over 2n minus 1 factorial times 2n on the top and the bottom, which gives us 2n times negative 1 to the n minus 1 over 2n factorial. And now these fit the same mold, you know? They both have the 2n factorial, which tells us that the 2nth derivative at 0 of the function is equal to 2n times negative 1 to the n minus 1. So we needed these denominators to match. And that's it. That's how we can find what the 2nth derivative of this function is using the Maclaurin series. 2nth derivative at 0 to be specific. Then the last example we didn't get to go through. This is actually a repeat from previously, but I want to go through it again and spend a bit, I don't know, give you an uploaded version of my explanations basically. So for this one, we've got the function is equal to 2 over x squared, and we want its Taylor series centered at 2. So again, we do know the general format of what the Taylor series will look like. Actually, I'll use the big highlighter. There we go. Okay. And so what we can do, wait, I don't know if you can see it. There's like a weird glitch. What's going on here? Well, there we go. Okay. So let's take some derivatives to get a pattern so we can see what fn2 is. Well, f of x, which is, its 0th derivative, we can say that's 2 times x to the negative 2. The first derivative, using the power rule, we get negative 2 times x to the negative 3. The second derivative, we get 2 times 3 times x to the negative 4. The third derivative, we get negative 2 times 3 times 4 times x to the negative 5. Just continuing to bring down essentially the old exponent and getting our new exponent. And this pattern is going to keep going. And so from here, we can see that the formula for the nth derivative looks to be, well, okay, the power of x that we have is like negative the derivative plus 2, right? So we can say that in the denominator, we have n plus 2. Because for third derivative, we had x to the 5. Second derivative, we had x to the 4, and so on. Then we get a negative for odd derivatives and a positive for even ones. So we should just have negative 1 to the n. Then there's always that 2, and then there's always that n plus 1 factorial. You can check if this works. This formula works for the fourth derivative, and I think that's what we did in class yesterday, but I'm not going to do that again. So, okay, that's our derivative for the fourth, or that's our formula for the nth derivative. So from that then, we know that the nth derivative at 2 should be equal to negative 1 to the n, 2 to the n plus 1 factorial over 2 to the n plus 2. We've got a 2 in the numerator, so we can do a tiny bit of simplifying. We've got negative 1 to the n times n plus 1 factorial over 2 n plus 1. And so from that, we can say the Taylor series we want is the sum of n from 0 to infinity, negative 1 to the n, n plus 1 factorial over 2n plus 1, n factorial times x minus 2 to the n. So we can say that's our Taylor series for f of x. Interval, I'm not going to do this one again. It's the last section. Did this. It uses ratio test, which again makes sense because looking at it, we've got all these factorials. Ratio test is a nice thing to use. Oh, you know what? I just realized we can actually simplify this a little bit more because we've got that n plus 1 and the n factorial. So negative 1 to the n, n plus 1, 2 to the n plus 1, x minus 2 to the n. Okay, so then we've got the estimation part. here we're going to estimate f of 3 with error smaller than 4%. So let's actually find what f of 3 is using this series. Plugging in x is equal to 3, we get the sum from 0 to infinity, negative 1 to the n plus 1 over 2n plus 1. And then instead of x minus 2, we have 3 minus 2 to the n. Oh, that's just 1. So this simplifies a little bit. We get the sum from 0 to infinity of negative 1 to the n plus 1 over 2n plus 1. And what we can do is we can start plugging in some values for n and just kind of expanding this out. So we get negative 1 to the 0, 0 plus 1 over 2 to the 0 plus 1, plus, same thing, but instead of 0, it's 1, n is equal to 1. So we have negative 1 to the 1, 1 plus 1 over 2 to the power of 1 plus 1, and so on. I'll give you what they end up actually evaluating to. We get 1/2 minus 2 over 4 plus 3 over 8 minus 4 over 16 plus 5 over 32 minus 6 over 64 plus 7 over 128 minus 8 over 156, and so on. Then, by the alternating series estimation theorem, the absolute value of the remainder is going to be less than bn plus 1. So find bn plus 1 being the first term less than 4%. Well, 4% is equal to 1 over 25. Okay, and we exclude from that term onwards. So looking at what we've got here, let's see. So 1 over 25 if we compare 7 over 128, that's going to be slightly larger than 7 over 140, which is equal to 5%, because that's 1 over 20. However, 8 over 156, that's equal to 1 over 32, which is about 3%. So this is that first term that we're looking at. So that means we'll estimate F3 with all of the terms before that. So 1/2 minus 2 over 4 plus 3 over 8 minus 4 over 16 plus 5 over 32 minus 6 over 64 plus 7 over 128. So here, these are the ones that we use to estimate with enough accuracy. And then this is the one that we exclude, if that makes sense. So let's actually check what level of accuracy we're dealing with. So I'll add up these fractions here. So, okay, I guess we have 1/2 minus 1/2. Plus 3 over 8 minus 4 over 16. When it comes to these like approximation questions, I always love seeing what the actual value is comparing to what we have, just because it's, I don't know, it feels so powerful to get this level of accuracy. Okay, let's see. So if I added this up correctly, this is equal to 31 over 128, which is 0.242185. Okay, then what we were actually trying to estimate was 2 divided by, wait, was it just 2 divided by 9? Actually, that's kind of funny because that's not, Okay, this is actually kind of a stupid question. F of 3 is 2 over 9. That's just 0.2 repeating. You don't need to do this for this. Okay, well, whatever. This is more interesting for what questions where it's not a irrational function, I guess. It's better for when it's like sine or exponent or something. So yeah, we can see that we're within 4%, basically. So yeah, I don't know. I don't know if you know this, but whenever you have something that's like k over 9 as a decimal, it'll be 0.k repeating. And then it's the same if you have like, you know, let's say 15, or not 15. I want to do something that's, okay, 17 over 99. That's 0.17 repeating, that kind of thing. Isn't that cute? So, awesome. Well, if you watch this, congratulations. I'll post the link to it in the notes, but you already knew that because you watched it. I should just stop. Okay, bye. See you in class.